We're excited to be back with another video on modeling in Abaqus using the USDFLD subroutine. We hope you found the previous videos helpful. In this video, we'll begin by explaining the problem at hand, then guide you through the step-by-step modeling process in Abaqus. Finally, by reviewing the results, we'll show how the USDFLD subroutine was used to capture the reduction in material stiffness when the sigma 1,1 stress component exceeds a value of 1. Stay with us. As shown in the figure, a cube with dimensions of 1 meter is considered in this problem. The material properties assigned to the cube are provided in the table. According to the table, if the maximum stress in the x direction is less than 1, the elastic modulus is 1 Pascal. Otherwise, it decreases to 0.25 Pascal.
Please note that the purpose of this video is solely to provide educational content. Therefore, for simplicity, we have assumed the elastic modulus to be 1. Since the chosen unit system is SI, metric, the elastic modulus is 1 Pascal. If the stress exceeds the allowable limit, this value is reduced to 0.25 pascals.
The Poisson's ratio is constant and set to 0.25. The boundary conditions are defined as follows. The back face of the cube is fully fixed, while the opposite face is displaced by 2 meters in the x direction. The objective is to analyze the stress-strain curve associated with the element of interest. To solve the problem, the general static step in Abaqus is employed. We will now enter the Abaqus environment and proceed with the modeling process step by step. In the Abaqus environment, we first set the work directory to the folder where the subroutine is located. After that, we need to define the cube in the part module. To do this, we click on Create Part and define a 3D deformable part. We also select the extrusion type. In this case, it's sufficient to draw a 2D square section and then extrude it. Next, we define a square with its first point at the center, 0, 0, and the opposite corner at the coordinates 1, 1. Now, when we exit the sketch, we input the sample depth, which is 1 meter. After defining the part, it's time to define the material properties. In the material properties section, we first define the number of state variables, which is 1 in this subroutine code in Abaqus. To do this, we click on dep bar and set the number of user-defined state variables to 1. Next, we need to inform Abaqus that the USDFLD subroutine will be used and that the field variable must be called from the subroutine. To do this, we select user-defined field. In the next step, we define the material's elastic properties, including the elastic modulus and Poisson's ratio. For this, we choose elasticity, and then elastic. However, as mentioned earlier, we want the modulus of elasticity to vary based on the field variable value. Therefore, at this stage, we set the number of field variables to 1. As you can see, in this case, the field column is also added to the material properties. Now, according to the table defined in the figure, we input the appropriate values in Abaqus. Next, we define a section and assign it to the part. Then, we go to the assembly module and create an instance of the part. Next, we go to the step module and define a general static step, which is used to solve static problems. Additionally, we limit the maximum increment size to 0.01 seconds to ensure there are at least 100 outputs per second, making the results visible. Now, we edit the field output and add the state variable to the desired outputs. In this case, by observing the state VI1 value, you can see where the stiffness has been reduced and where the absolute stress in the one direction remains below 1 Pascal. Next, we go to the load module and apply horizontal displacement along the x-axis to the front face of the cube. In the problem definition, a displacement of 2 meters is mentioned, but you can increase it, for example, to 2.5 meters. However, if the displacement is too small, the stress may never exceed 1 Pascal. Finally, we fully fix the back face of the sample. Finally, go to the mesh module, set the object type to part, and create the elements. Since the goal here is to examine the material stiffness mesh under the effect of increasing stress, only one element is created. Therefore, the element size should be set larger than the cube dimensions, i.e. 1, and then the element can be generated. However, You can choose smaller dimensions to examine other issues. Next, we go to the job module, select a job, and then choose the Fortran file, which we previously explained how to create in the earlier video. Now, we submit the job and wait for it to finish so we can review the results. What we want to check in the results is the stress-strain curve to determine whether a reduction in stiffness has occurred when the strain exceeds a value of 1. To do this, we click on Create XY Data, then we select the ODB field output and set the position to Unique Nodal. Since we are interested in stress and strain along the x-axis, we choose E1 and S1, which represent the strain and stress in the x direction, respectively. Next, we click Edit Selection and choose a point on the plane that is being drawn. Afterward, we click Save to store the components as they are. Then, we click on Operate on XY Data and plot the combination of stress and strain. According to the curve, when the stress reaches a value of 1, the stiffness, determined by the slope of the curve, has decreased. Based on this, the reduction in material stiffness in Abaqus, following the specified criterion, is accounted for using the USDFLD subroutine.
This was a very simple example in which we aim to teach you step-by-step how to write the USDFLD subroutine and call it in Abaqus to solve a problem where the elastic modulus depends on stress. This example can assist you in developing the USDFLD subroutine for your own project. However, if you're interested in diving deeper into this topic and want to learn how to write the USDFLD subroutine for more complex and realistic examples and gain full mastery over all its parameters, we recommend checking out our training package via the link in the description. Additionally, if you'd like to access the abaqus.np file and the Fortran subroutine code used in this video, you can download them for free from our GitHub page. The link is also in the description.